Okay, so let's look at the impact of our next factor, catalyst. Okay, and so first we'll look at the demo, and then we'll talk about what's going on. So here we have in our Erlenmeyer flask 30% hydrogen peroxide. Now when it undergoes decomposition, it will release hydrogen gas. So what we'll do is add a bit of soap, and this will allow us to capture the gas and some food coloring so we can see the foam. So as we can see here, my hydrogen peroxide is not decomposing. As I add my catalyst, though, it goes from decomposing at a very slow rate to a much faster rate of decomposition with a very exothermic reaction. Okay, so we can see the catalyst resulted in a change in the rate of the reaction. Well, a catalyst is a substance which causes a reaction to occur much faster without being consumed itself. And the way that this occurs is it provides an alternative way for the reaction to occur. And this new way of it reacting has a lower threshold or activation energy. So reactions can occur in a series of steps. They generally do. And so what a catalyst does is it provides a different series of steps. So similar to how we added our Hess's law equations together, a catalyst gives us a different set of reactions that we could add together. And this different set of reactions causes or requires a less amount of energy for the reaction to take place. Now we can classify our catalysts into two types, being either heterogeneous or homogeneous, and it just depends on the relationship of their states to the catalyst. So for example, platinum wire in a catalytic converter of your car, which helps to ensure that any nitrogen oxide compounds that are formed are nitrogen dioxide, it would be a heterogeneous catalyst because it is solid and the substrate or thing that it acts on was a gas. So since their states are different, that would make it a heterogeneous catalyst. Whereas in the example we just saw in the video, where with the decomposition of my hydrogen peroxide, the catalyst, the potassium iodide, and the peroxide were both aqueous. And so as a result, since their states are the same, it would be classified as a homogeneous catalyst. So similar to what we did with temperature, we can use our Maxwell-Boltzmann curve to look at the impact of a catalyst on the rate of reaction. So again, if I have a reaction where it has a reaction pathway which has a really high threshold or activation energy, not a lot of particles are going to have sufficient energy for effective collision. But if I add a catalyst, what it does is it would reduce that threshold or activation energy. And this changes my number of particles with a sufficient amount of energy for an effective collision, where I went from just a small fraction to represented by the red, all of the area under the curve past the first dashed line now would be particles with enough energy for effective collision. So by greatly increasing my fraction of particles with effective collision, it allows for a greater rate. Okay, I'll turn the reaction pathway. Okay, and now, so this is one of the ways that it does it. The second way that a catalyst can impact our rate of a reaction, it would be that it just helps to ensure the correct orientation. And so what it does is it allows for the particles to collide in the correct orientation. Well, again, this means that we have a lower threshold energy because they're colliding in the right way. And also it would increase the number of collisions with correct orientation, so higher fraction of effective collisions. And we can especially see this type of catalyst when we look at biological enzymes, because biological enzymes, they grab our two substrates, they bring them together, and they make sure that when they come in contact with each other, they are positioned correctly. And as a result, they don't require a large amount of energy. Let's take a look at the impact of surface area. We have a number of video demos, and then we will look at the impact. So here we're placing lycopodium powder on a sheet. Okay, and so we will, as you can see, if we light it, it's a very slow rate of reaction, and it doesn't burn very easily. But if we were to take that same amount, lycopodium powder, we'll put it into a funnel, put that in the bottom of the can for safety. And what we're going to do is we're going to aerosol it or cause it to fill up the space with and increase its surface area. Okay, and so we'll use a candle as our ignition source. This will help to cause the powder to aerosol. And so when we do this, we can see a much faster reaction. Our second demo for this would be the igniting of steel wool. So if I have steel wool being iron, if I had iron on a bench and I brought a flame source to it, it wouldn't burn very easily. But if I increase its surface area, like in steel wool, and I introduce a source of ignition, we can see that it will go through a rapid reaction with oxygen or undergo a combustion reaction. Our last demo is looking at the impact of ethanol. And so what's being done here is a tiny bit of ethanol was placed in a jug and is being swirled around in a jug to cause the vapor of ethanol to fill the container. Now, ethanol has a relatively high volatility, especially in its pure form. So we're just vaporizing, just rolling it around and filling the container with it. We'll drain off any excess liquid ethanol remaining for safety's sake, because we don't want to get in danger. And when we add our source of ignition, we can see the rapid reaction. You can see the flame go down and it'll undergo rapid combustion. Now, when we're looking at solid particles or even gases, they interact when they can come in contact. So if I have a substance with a boundary layer, for example, a liquid or a solid, only the particles on the surface can collide, but the ones in the center are protected. Whereas if I take the same amount of particles and split it up, I could increase the potential for interactions and allow for more collisions. Okay, so again, rate is proportional to our surface area. As we increase our surface area, we get a greater number of exposed particles. More exposed particles allows for more collisions. More collisions allow for a higher rate of reaction.